Hi, everyone. My name is Carmen Jackson, and I'm on the Android performance team at Google. And today I'm going to talk to you guys about debugging application performance. So, like I said, I'm on the Android performance team, and it's our goal for the phone to seem magical to the users, right? Fast, smooth, intuitive, responsive. And for that to happen, we need to be on point with the system, and we need to be on point with the apps. It really only takes one slow app to make a person think that their phone is slow, right? So it's kind of up to all of us to keep things in shape and maintain Android's good reputation. But when we say good performance, what do we mean? First, 60 frames per second. So 60 frames per second is the magic number for smooth interaction. As long as you can get your work done in time to draw the next frame, you're good. But if you drop one, users will notice, and they really will, even if you just drop one, and that's what we call jank. And second, we don't want our users to have to wait. And the most common time they might have to wait is during app startup. So we make it our goal to minimize the downtime when switching between apps, and minimize the amount of time before that first app frame is drawn. At work, I spend a lot of time making sure that we keep background processes or background apps in memory as long as we can, so that when that app is restarted, it's a fast, warm start. When we can't do that and an app is killed in the background, or of course when it's the first time an app is opened on the system at all, we need to make sure the cold app starts are as efficient as possible. And a lot of that effort comes from you, the app developers. And that's really it. With just those two goals in mind, everything else performance-related just kind of follows. So who here has heard of Systrace? Cool. Who here has used it? All right. Who has discovered a big performance win using Systrace? All right, so that's a little bit less. So I'm going to try to bring that number up a little bit. Systrace, is this working? Systrace is the Android performance team's favorite tool to use. So we're all really familiar with the code that we write, right? And we know what it does in general. But I've found across the board, from apps to the Android platform to the entire system, sometimes we're wrong. Sometimes, frequently, something is influencing our code that we don't expect. So like if you have an A/B test running or an experiment running, or you depend on a library and maybe you've updated that library and it has changed, or you're calling into a framework API. And sometimes we're surprised by the amount of time something takes. So like we knew exactly what we were doing, but we kind of didn't know it would turn out like that. So when we look at Systrace, Systrace shows you a very, very precise picture of what's happening, all the way down to the individual CPU time slice, so sub-millisecond. Once you're looking at that, you can make much, much better informed decisions about what's going on your code. And then you can make well-informed trade-offs as well. What do you want to do? What is worth it to change? So just to make sure we're on the same page, I'll remind you all what the trace viewer looks like. When you open a trace up, this is what you see. So you're on a timeline, left to right, and you can use the WASD keys to scroll left and right and zoom in and out of your trace. These tools in the upper right corner are a little palette. You can click the tools, or you can use the numbers 1, 2, 3, 4 on the keyboard to select between them, which is kind of the next level wizardry way to do it. So if you use the first tool, it's a selector arrow, so you can select things singular or in aggregate and view information about them in this bottom info section. Tools 2 and 3 are for panning and zooming. So some people like to use those instead of WASD. They're a little bit smoother instead of jumping. And the fourth tool is for selecting a region of the trace. So it locks to the edges of the adjacent views to let you kind of get an exact representation of the amount of time something takes. And you can also use the letter M to lock to the edges of a single view. So if you have selected a view and you hit M, it will select just that view. So when you've selected a section or a view, that'll look like this. And I use this all the time to select an area of the trace that I care about, and then scroll up and down through the trace to see what else is happening during that period of time. So as you scroll down, each section below this top kernel section represents a process that's running on your device. So here at the top, we can see the Surface Flinger process running with PID 627. And then each row inside that process represents either a thread or a trace counter that's running in that process. So today, I'm going to share with you some tricks for investigating app startup performance. And I'm going to focus on startups specifically because it's a little bit easier to draw conclusions about app startup on a general level. When you're debugging jank, it's going to have a lot to do with the specifics of your app. So you'll probably want to add some trace points, in-app trace points inside your app to add the context of what you're trying to do inside your app during each frame. For app startup, the platform level trace points are good enough to give us some good debugging information and really show us what's going on without requiring app-specific context. So I've redacted any app-specific information, but I got these startup traces using apps on my personal phone. So a lot of you say you've looked at traces before. There's a chance you'll recognize your app in here. So first thing you do when you're trying to look at an app startup trace is go into your trace and locate the launching section for your app. And so that's going to be located inside the system server process. And you can find it by using Control F to search the page. So you'll select that with the 1 tool and hit M to highlight it. And this time represents your startup time until the first frame of your app is drawn. So then you'll scroll down into your process to the UI thread of your process, and that's what it'll look like down here. This is generally what I expect to see from an app that just has a straightforward, simple app startup. So first we'll see bind application. And this pink section inside bind application is going to be the system opening up your APK and loading in your DEX files. And then over to the right, we'll see activity start, activity resume, the choreographer laying out your first frames. And then the timer continues until the first frame is successfully sent from your app. So you can see that this F in the green circle represents the first frame being successfully sent. And so the first thing that you do when you are taking a look at your app startup, or really when you're taking a look at any trace that you're trying to evaluate the performance of, any area, is to examine the critical path. Just look at the top level, what is being traced, what is happening here. So in this case, here are 2 different app startups that are actually starting extra activities in the process of their startup. So this is actually super common. And the question you need to ask yourself as an app developer, if you're doing this, is it worth it? So the first one adds 235 milliseconds to their app startup starting this first activity. Second one is adding 166 milliseconds starting that first activity. There's a few reasons we might see apps doing this. The first one that comes to mind is showing a splash screen. But a lot of apps will also do this to show a permissions page or a login page if they need it. But if they don't need it, this first activity just turns into a pass-through to the activity the user really wants to see. So if your goal is to do a splash screen, there's kind of another solution to that called a launch theme. And that's a specific theme that only applies when you're launching your app. If you want to do permissions or a login page, that's a little bit more complicated, but you could use, like a module that you code up and a base activity class to do that check and only open the second activity if you need it, rather than opening it every time. Either way, if this is a strategy you've decided to use, here you can kind of see exactly how much of an impact that's really having. You can decide for yourself whether that's what you really want to do. So I had to zoom in to the top-level critical path in order to see this one. But service transactions are also on the top level of your app's critical path. So these will also delay the first frame from being drawn. And the absolute value of these is pretty small. So it's 8 milliseconds for the top one and 11 milliseconds for the bottom one. But even that small amount adds up. I would fix a 10 millisecond app startup regression. And for some services, this might be worth it. Some services you need to start immediately while your app is starting up. But for others, you might be able to move this start outside of the critical path or after the first frame is drawn with no impact to your users. So definitely something else to really consider. After you've looked at the top-level critical path when you're performance debugging, you'll want to dig a little bit deeper. And this is one that's super common recently, so I wanted to call it out specifically. Apache is no longer included in Android P. So inside bind application, where you can see your APK index files being opened, you might also see Apache being loaded as well. So you can see that in the trace, it's taking 17 milliseconds. In P, the Apache library is removed from the default class path. So if you're using this, it now needs to be loaded in additionally. And especially if it needs to be paged from disk, we can see that it can take a long time. The recommendation, as it has been for a few years, has been to switch to HTTP URL connection. And I'm really sympathetic if that's not something you want to do, because HTTP URL connection is not similar. But it might be worth it at this point now that there's a performance impact. If you're already thinking about app performance, then paying attention to what views you're inflating is probably not news to you. But examining them with Systrace to see what their actual inflation times are can really help you prioritize what's important. And this is definitely an area where there's a ton of performance advice floating around. And I've watched all those Colt McCandless videos, and I'm sure it's all good advice. But there's no substitute for actually looking at the numbers and seeing what your views are actually using. So in both cases here, there's a whole lot of views being inflated. In the first app, this might be a little hard to read. This long view that's being inflated is called the welcome screen address bar. And there are a whole lot of nested views inside this address bar. There's 4 different sub-inflates in there. And only the developer would know for sure, but when I loaded up this app and I looked at what was drawn on the first screen, it did not have this many views in it. So there might be something more complicated going on. I can also see that app-based libraries in this view, so it could be a more complicated view that only some parts are enabled for, or it could be a view where the developer has a lot of components of the view that are hidden, kind of waiting for the user to interact with it in some way. But either way, here you can see they're making a pretty big trade-off to kind of be ready for that. Down here in the second view, we're seeing a drawer being loaded. And so it's a modern drawer view. And it's taking up about half of the total time for inflates in this activity start. It's taking up about 42 milliseconds. Drawer views are really interesting. They're kind of a conundrum because it's possible for someone to open up your app and then really slam on that drawer view and open it up right away. But drawer views almost always have a ton of child views, right? That's just the UI of them. And it takes a lot of work to get them ready in advance. So whenever we load a drawer view proactively inside activity start, we're making a little bit of a trade-off between having every user absorb the inflate time for that drawer, rather than have the occasional user who tries to load it immediately, seeing a small delay. And that's a hard question to answer. But again, interesting to note that this is kind of the size of that trade-off. When you're looking at views, another thing that often jumps out at you real fast is large images. And I'm constantly surprised when I open up traces and I see these giant images being loaded. So here, both of these look like, based on the name, that they're background images. The top one is a background search welcome.webp, and the bottom one is background_afternoon.ping. One's in activity start, the other's in activity resume. And it's really possible these app developers, or the designers they work with, really wanted these beautiful, detailed, gorgeous images in their app startup flow, right? But 50 milliseconds is objectively kind of a lot of time in terms of app startup. And so these developers should be really aware of the trade-off they're making And consider this a really good opportunity for optimization here. First off, you can almost always replace a ping with a WebP with no visual change, but you'll see often a size improvement, often a load time improvement. So that would be a good immediate suggestion to make for this app developer. And then second, in a case like this, I'd really recommend that you play with your image quality, toggle your compression up and down until you find something that balances an image quality that is what you want to see with the loading time impact that you're going to have. And one specific thing I want to call out about large images that I see a lot is that we'll often see them on splash screens. And that's a real dilemma, right? Because on one hand, the splash screen is just there to bridge the gap between your loading time and your activity being started. So on the other hand, if you're slowing down and blocking your activity being started by showing a huge detailed picture in your splash screen, you're kind of fighting with yourself a little bit there, right? So that's a really common thing. Once I've kind of taken a look at what trace points are in there on the top level, kind of on the second level, the next thing I'll look at is the state of the UI thread, or the thread that I'm trying to debug or performance evaluate. So the thread state is this narrow row on top of the threads row in your Systrace. It kind of looks like confetti with just all these colors everywhere. And there's 4 main thread states that you'll want to know about. So the green one is running, which means a thread is scheduled on a CPU right now. And you can see when you click on a green segment in the thread state, when you click on a green thread state up there, you can actually see details about that CPU time slice in the information section at the bottom. So you can see how long is that time slice running for, when it started, which CPU it's on. The next thread state we're thinking about is runnable. So that means your thread is ready to run, but it's not scheduled yet. Sleeping means your thread is not eligible to run at all, which usually means your thread is waiting on something like a response from another thread. Often this is something like a binder transaction. So if you take a look at why your thread is sleeping and you track it to the other process, often that other process is just continuing and doing the work that you asked it to do. But it's always good to kind of double check that when you see sections of threads that are sleeping. And then the last one we're thinking about is blocking I/O. So blocking I/O means that you're reading from disk. If you use the number 1 tool, select a section of the thread, you can actually view aggregate data about the thread state, and that can really help you get a quick kind of mental image if there's any bottlenecks going on in that section of your code. So if you select the whole area and you see that it's always running, the majority of the time is running, but you still feel like that code is just objectively executing too slow, that just means that you need to optimize what algorithms you're using. So take a look at the libraries, take a look at your data structures, and see where you can speed things up that way. If you are sleeping a lot, you'll need to check the other threads that are running to make sure they're doing the right thing, to make sure there's no gotchas elsewhere where you're not looking. If you see a lot of blocking I/O, and I'll talk about this a little more in a second, you'll want to look at what libraries and files you're loading and see what you can optimize there. And if you're seeing a lot of runnable time, the system is scheduling other things ahead of you. And specifically, I want to call out for runnable time, you should never see a lot of runnable time in a UI thread for a running app. But if you're trying to debug performance on a background thread, you might see a lot of it. And that's a kind of red flag that means you have set the priority incorrectly on that background thread. So if you're looking at a background thread, it's too slow, it's always runnable. It's maybe not really as background as you thought it was, right? It might need a higher priority. So here's an example of a case where there's a huge gap where the thread is sleeping. And rather than just see like, oh, it's a binder transaction, like the work continues elsewhere and we came back, here, this activity resume is seeing monitor contention. So when you notice monitor contention in your trace, you can click on the trace segment and see an explanation of where exactly that monitor contention is happening in the code. So here it kind of looks like RxJava is owning a lock. The monitor contention is the same as lock contention. So RxJava is owning a lock of some sort, and then it looks like this, whatever app this is also using retrofit, and there's some kind of monitor contention going on there. So these are often actually transient errors, so you might not see a lock contention like this in every trace that you take of your app, but if it happens once, it can happen more, and so this would be a flag for the developer to take a look at how they're using these libraries, see if there's a way they could like restructure their app setup to avoid the potential for this contention. So here we see a section where where we're seeing a lot of blocking I/O inside activity start. So 25 milliseconds of blocking I/O almost all at once is a really long time. And the best recommendation for how to figure out what's going on here is to add some in-app trace points to identify what's being loaded into your app at that time. And what I'll always recommend, often this doesn't produce any results, but what I'll often recommend is to start off by doing a little light evaluation of your library usage. So if you're calling a library but you're not really using it, or you're just loading it in to call one function, or do like one little bit of complicated math or something like that, maybe there's alternatives or workarounds that will allow you to like completely cut the dependency on this library that you're loading in. So that's always worth checking. Another thing when you see sections of long I/O like this, that's always kind of a surprise is if you scroll down, here we can see that there's 3 other background threads on this app that are doing I/O at the same time. We have a scheduler for prioritizing the UI thread on the CPU of Android devices. And on a CPU, we have multiple CPUs, so we can actually parallelize that work. Most Android devices only have a single I/O channel for doing these requests to disk. So sometimes the I/O from a background process can occur ahead of the I/O you're trying to prioritize in the foreground process, just because they're competing with that time on your one I/O channel. So it's really common to see app developers being proactive about doing background threads, especially background view inflation for views that they're not using right away. But those view inflations will still access the disk. And so sometimes, even though you're kind of trying to get ahead of the game there, you'll start kind of stepping on your own toes by blocking the I/O in your main thread from your background threads. This is super common, and it's really worthwhile to be thoughtful about when you see something like this. Can you move this I/O-heavy background work to later on in the app startup process? Can you kind of wait to start those threads until after you've drawn your first frame or a little bit later in the app startup with no impact? That might be really worth it to do. So there you have kind of an outline of how you might use Systrace to analyze your app and try to turn up some performance issues. And I want to emphasize that all of these strategies, I applied them to app startup, but I'd use the same strategies if I was trying to evaluate the performance of any segment of an app at any time. So before I leave you, I'll briefly go over how you can get these traces for your own app. And the first thing that I want to call out is I've mentioned in-app trace points. And adding in-app trace points is super easy to do. So we have the Android OS Trace API, and it has only 2 functions in it, trace.begin section and trace.end section. And inside trace.begin section, you add a string that's a label to that trace section, and that'll just show up as a trace point in the trace HTML, just like you were looking at before. The string that you write will be the label there, and this might seem obvious to you, but I'm definitely going to call it out. You can add variables to that string, and that can be super handy. Actually include the name of the file you're loading, or the name of the image, or stuff like that. Also, you can nest these trace begin section and trace end sections, and they will kind of stack as you would expect, like a flame graph in the trace that you end up taking. So the first way to actually take a trace from your device is called Catapult. And Catapult is actually included in your Android tools, but I prefer to recommend that you actually, it's open source, so I prefer to recommend that you go ahead and clone the GitHub project so you can get whatever are the actual latest updates to Catapult or to the trace viewer. And so all you'll need to do is clone it and then run this systrace command at the bottom. And this, you'll need your phone plugged in. This operates via ADB, and it will take the trace and output it into the HTML file that you've supplied. So this giant list of arguments is trace categories. And this is actually the list of trace categories that I would recommend for getting relevant information out of your apps. So these are kind of the good ones. And also, I want to specifically call out this -a argument. So if you've included in-app trace points, you'll need to include this -a argument with your package name, and that app has to be compiled as debuggable for Systrace to see those trace points. And that's for security reasons. We don't want people to, if you have accidentally included app trace points in your app and then shipped it, other people won't be able to read those because that app won't be marked as debuggable. The second way to take traces is to use the on-device Systrace app, and that's located inside developer options at the bottom of the debugging section. And so you don't have to be, the difference is that you don't have to be connected to ADB to use this. So you can open up the app, set your trace settings, add the debuggable applications flag, pick categories, and so on. And you can even add a quick settings tile to your quick settings panel so that if you are just kind of out and about and you notice your app acting bad, you can quickly start a trace, record the bad interaction, and then stop it and save it. So I definitely use the quick settings tile every time. Once you have finished taking a trace, it will show you some notifications. I'm taking a trace, I'm saving a trace, and then it will ask you to share it. So you can share it through kind of the normal share sheet via email or Google Drive or whatever. Or you can plug in your phone later and pull all the traces down with ADB pull in data local traces. Once you've done that, this tool generates compressed trace files, .ctrace files, because these HTML files are like 250 megabytes. They're massive. So we'll output these .ctrace files, and you'll need to run them through this quick post-processing script, systrace -- from file, to create the HTML files to view them in your browser. And last, I would be kind of remiss if I didn't point out Android Studio's CPU profiler. So you can view a lot of the trace info that I just shared with you via this UI in Android Studio. If you prefer to use Android Studio, if you're familiar with their profiling tools, this might feel better to you. It's a different trace viewer, but it's showing the same information from the traces. It's a little bit more closely targeted towards showing only your app and only your app's process. So it's just a little bit of personal preference whether you prefer Android Studios or whether you prefer the traditional HTML trace viewer, which has, will maybe show more information, but you may or may not care about that information. So here's another option for you for viewing traces. And that's about all I have. And so I do have a bunch of time for questions if anyone has any. So I think your question was, it's pretty normal to inside your start activity to fire off your initial RxJava request. And does that seem like a problem? I don't know if I've looked at a trace for that, and I would definitely want to. I think the question would be, when you fire off that initial RxJava request, probably how much work gets done, setting up RxJava initially and sending out that request. And does it get in the way? So I would say I don't know offhand, but I would definitely recommend look at a trace and see, put a trace point around that RxJava work, look at a trace and see, is that work actually blocking, or is RxJava doing the right thing and putting that on a background thread that's operating correctly and staying out of your way? Does that make sense? So in general, generally speaking, should you defer network requests? I haven't generally seen kicking off a network request take a lot of time, because that usually does pretty quickly switch to a background thread, right? So in general, my guess would be that you don't need to defer something as simple as kicking off a background network request. But like I was saying before, you kind of never know. And that's kind of the main thing that I want to emphasize to everyone with when you're thinking about the performance of your app and when you're thinking about using Systrace is, I think it seems okay. But you would really need to take a trace of it, look at where that network request is happening, see how long it really does take, because it's going to take a little bit of time, and you'll probably think, oh, that's okay. But you should know for sure, right? So it's probably okay, but check on your own. Thank you. That was a good question.
I'm actually quite new to Systrace, so when I first looked at the tools were confused.
Yeah, so he's kind of asking, when I'm looking at a trace like this, let's get a little bit more specific about what exactly are we looking at. So bind application is one thing that's happening, and then anything that's underneath that is kind of a nested function that's happening within bind application. So when you look over at the activity start and you see underneath it the inflate is happening inside the activity start. So if you think about tagging, the activity start is tagging the beginning and the end of the activity start function, and then anything underneath it is happening during that activity start function. Does that make sense? Does that answer your question? Oh, yeah. So, I think I don't have a super good, if I go a little bit, so here's a case where like a bunch of stuff is nested, right? Like you're seeing the APK is getting open, and then inside that, a part of that work is open dex files from oat. Part of that work is the pink and green underneath that. Let's see. So he was asking, just kind of when we're looking at the nested trace points, what are we seeing there? So here's an example of where we're seeing several threads which happen to be in the same process. This is what several threads look like. And so the top one, the UI thread, has an activity start trace point, and then nested underneath that, it has several other trace points that are happening during that activity start. These other threads look different because they don't necessarily have trace points that describe the work that's happening on that thread. So that's why inside the selected area, there's no box with words under it, because there's no trace point there to define that area.
That explains how if you added the trace points with strings, they would come up with actual boxes.
Right, so as he was saying, when you add a trace point with a string, it would come up as an actual box with words. So if this was a section of your app that you added a trace point to and you'd add those words, then you would see a box here underneath these orange sections describing what was happening. But there doesn't happen to be a system trace point for that section describing what's going on there. So all we can see is the narrow thread state. All we know about it at this time is the state of the thread, which is doing blocking I/O. So the answer to that is kind of complicated. So the question was, in the new Systrace tools, which are in Android Studio, they'll show the frame which is being rendered. And do they show that in this Systrace? And the answer to that is kind of complicated. The short answer is no, it doesn't show it in a very convenient way. But the longer answer is when you're looking at a trace of your activity start, so these kind of Fs inside the circles represent when your process is trying to send a frame up to the surface flinger, which is the process on the device that consolidates all the frames that are being sent from all of the visible processes. So your app, system UI, and so on, consolidates those and sends them along to the hardware composer. So you can see here your app sending, working on each frame and sending its frames up. And you can use those Fs in a circle as kind of a guideline. You can also scroll up to Surface Flinger, the process that receives them, and look at the work that Surface Flinger is doing and see its work per frame. So so you can access all of that information inside this trace view. The Android Studio trace view simplifies it a little bit and makes it a little bit easier to see right next to each other how your app's work relates to Surface Slinger's work and so on. Does that make sense? Great. In the back. Yes, so his question is there a way to get a text file or a JSON file from the Systrace instead of HTML because he wants to do some processing on the trace instead of view it visually. And that is huge. That's an awesome idea, and yes, you can. There's actually, inside Systrace, there are two scripts. One is called trace2HTML with the number 2, and one is called HTML2trace. The HTML files that get generated actually include the trace file in text inside them. So you can use those files to convert, to basically take off the HTML wrapper and put it back on. So yes, you can definitely access the trace file as a text file. Unfortunately, whether we can get that in like a more convenient text file like JSON, the answer is no. So the trace files have a particular trace format. There are open source libraries for processing the trace format. One is called Trebuchet, because it's related to Catapult. And so if you're interested in doing that, I would definitely recommend checking out that Trebuchet library for trace parsing. Come see me afterwards, I'll spell it for you, Trebuchet. Do you have a question? So with regards to app startup, how is your code loaded into memory and how does that affect app startup? Over here is where your code is initially loaded into memory. And then throughout app startup, as it uses, so it'll load your APK files, load your DEX files here, and then throughout the activity start, it will load the XML files and things that you use, libraries that you call into memory as well. Sorry, did that answer your question about how it loads into memory? No, sorry. It will load your DEX files, but it will not necessarily load your entire APK. I would actually need to look that up because I don't think it loads in all of your bytecode. I think you can optimize, because I think you can optimize out what exactly it loads. But I would have to check on you for that. Yeah. And then it loads the rest later. Yeah. I would have to do some research on exactly which is loading in here. Maybe you're a little bit more familiar with it actually, but I know if you have multiple DEX files, it will need to load in the secondary DEX files later. If you call a library or you have XML files that are being inflated or loaded in or whatever, it also loads them later when you use them. So it's not loading in every library or every XML file that you have right away. It's kind of loading them when they get accessed. Yeah, sorry I didn't have a complete answer for you there. Anyone else? Any other questions? I think if I were to do it, I would do a background thread. I would be nervous about waiting a certain amount of milliseconds, like waiting a set amount of milliseconds. But I might do it on a background thread that gets kicked off later in the process, or even look at a callback for the frames being drawn, like do it in an on-draw callback or something like that. Yeah, probably one of those two. It's been a minute since I actually wrote that code, though I have before, but I think there are a few different options for what you might want to do. Also, depending on the amount of activity that you have kind of at the beginning, or the amount of, like you might also be able to get away with waiting until the person clicks on the drawer to open it, depending on whether there will be a visible delay once you factor in the animation at that time. So that would maybe be an easier thing to do if your UI can support it. So this question was, since we only have the one I/O channel for reading from disk, are there other areas where we're restricted like that, where multi-threading won't help us? Not that I have come across. I think there might be a similar contention if you are trying to interact with some other kind of hardware, like another kind of sensor or something. But I see the I/O stuff so often that people are not generally running into that elsewhere. So nothing comes to mind. Can you run these traces on the emulator? And if you can, is that data meaningful in any way? So if you use the Android Studio CPU profiler, it's actually really easy to take those traces on an emulator. The data is, I would characterize it as kind of meaningful. It still lets you figure out what's happening. It shows you what's happening. So if something really surprising is happening, I didn't realize I was, calling out to this service, or that I was inflating so much stuff or something like that. Yeah, that's useful. But since it's not information from an actual device, the actual absolute values of the times are not as useful. So when you're using, when you are using an emulator, you kind of naturally have to take it with a grain of salt, understanding that that's what you're doing. But I still think it's really valuable it's always really valuable to look at a trace of your app and kind of map your mental model of how you understood your app to work with what is actually happening in the trace. And that's valuable whether or not you can 100% trust the numbers that go with it, if that makes sense. Thank you for that question. So if any of you guys have any more questions, or if you want to go over a trace of your app with me, I actually have office hours in the Koblenz room in an hour at 3, from 3 to 4. If you have more Systrace questions or general system performance questions, come over there and we can chat. Thank you.